Welcome back. I'm going to be re-recording this question because I did a little bit of an oopsie. Let me really quickly remove any notes that I was taking for myself. All right. So to kick it off, so this question is about reverse engineering cache. In other words, we're going to look at an access pattern, and using strictly that access pattern, we're going to be able to determine information about that cache. So that's things like the block size, the addressability, and the total size of the cache. God, I got bags. Okay, so the first question says, look only at the first three accesses. And using only these first three accesses, we're going to determine the smallest possible range of block sizes. So let's take a look. So that first access that we see, and we're accessing C0, that was a miss. Assuming the cache is empty before that, no matter what access we're doing, that's going to be a miss. And so that doesn't really tell us very much information. Yes, it's a compulsory miss, but it's like we don't learn anything from it. However, from here on, if we see any hits, right, that means for at least addresses that have never been used before, that means it must belong to the same block. So then on access 2, we look at address C1 and we get a hit. Now, if we didn't know block sizes, we didn't know that we brought stuff into our cache as blocks, this would be really strange to us because I've never looked at that address before. However, because we do know about blocks, this must mean that C1 belongs to the same block as C0, right? So we know that they belong in the same block. How can we use that to determine a lower bound for the possible range of block sizes? Well, we can look at their binaries, right? So if we look at their binaries, we see that the most significant bit at which they differ is going to be this last bit right here. And so because they differ at this last bit, we can determine that the block size is going to be 2 to the essentially the place of the bit that we're looking at, which is 1. So the minimum block size is going to be 2. Because if I change the last number, only the last number of an address, then the range that I'm looking at in terms of numbers is 2 different numbers. And so the smallest possible block range that the smallest block range that we're looking at is now we kind of have a lower bound of 2. But that doesn't tell us anything about an upper bound. As far as I'm concerned, if I've only looked at these 2 accesses, my upper bound is unlimited. I could make it massive. So let's take a look at address DE. So we look at address DE and we see that we get a miss. So what does that mean? Well, so far, what I know is inside my cache, I only have 1 block, right? Because C0 and C1 belong to the same block. And so when we get a miss here, that tells me essentially just that DE doesn't belong to the same block as C0 and C1, right? So then very similarly, we can go and compare these addresses, and we see the most significant address at which they differ is that 5th bit, right? And so what does this tell me? This tells me that if any 2 addresses have different 5th bits, they can't possibly belong to the same block. In other words, they possibly could have 4 matching bits, right? If those 4 differed, that might be fine. I don't know yet. But I know for a fact that if I look at an address and its 5th bit is different than the 5th bit before it, they belong in different blocks. So to determine what the upper bound of the block size is at this point, we know that it could possibly be 4 matching bits. And so the number, because note that our block size bound is less than or equal to. And so we're going to use 2 to the 4th. And so that'll be 16. And so the justification that we'd write here, I'm not going to do it, but it is kind of explaining how the different access patterns resulted in our conclusion. So you'd want to reference like access 1 and 2 to help you determine lower bound, and maybe access 1 and 3 or 2 and 3 to determine the upper bound. So moving on, I'm gonna go ahead and switch colors. So for number 2, it says looking only at the first 6 axes, you're able to determine the block size. So in other words, we're going to continue the same thing that we were doing earlier, except our bounds are going to converge. Our lower bound is going to end up equaling our upper bound, and we're going to be able to determine exactly what that number is. So let's pick up where we left off. Okay, so now we're going to be looking at this entire range. And so the first new axis that we introduced is C1, right? C3, and that's a hit. So what does that tell us? Well, again, I've never looked at C3 before. And the only possible blocks that I have in my cache right now, I have 2 possibilities. I have C0 and C1, and I have the block for DE. Now, I don't know, the block for C0, C1 could be evicted at this point. I'm not certain, but I get a hit here. I get C3 as a hit. Well, I know that C3 doesn't belong to the same block as DE, right? Because that wouldn't fit in my upper bound. They have different fifth bits, but I still get a hit. That tells me that my cache has both the blocks associated with DE as well as the block associated with C0, C1, and now C3 in it, right? Well, if C3 belongs to the same blocks as C0 and C1, let's look at their most significant different bit. And so that's going to be the second bit here, right? It has a 1 as opposed to the 0 as from earlier. And so now we have a tighter upper bound, right? We go from 2 to the 1 to 2 to the 2, right? So 2 to the 2 is our current lower bound. Great. Then we're going to look at the next axis, which is DF. And we get a hit. So this isn't all too surprising because DE we know belongs in the cache right now. C3 couldn't possibly have caused an eviction. And so let's see if we can get any information at DF. So DF is a hit, right? So that can only potentially increase our upper bound, but we don't know that it's going to. So let's look at the matching bits between the first different or most significant different bit between address accesses 3 and 5. It looks like it's just going to be that least significant bit. So what does this tell us? Well, this again tells us our lower bound is going to be 2 to the 1, right? Or a lower bound is going to be 2 to the 1. Well, that doesn't tell us very much. We already have a lower bound that's bigger than it, right? We have 2 to the 2. That doesn't give us any information. And so axis 5 just doesn't give us very much information with respect to this question. So then let's move on to question 6. So, or access 6. So then in access 6, we access C7, right? So what do we know belongs in our cache right now? We know that both the C0 to C3 block, as well as the DE/DF block are in my cache. I know that with certainty. So then when I get access C7, I get a miss. What does that tell me? Well, it tells me that C7 doesn't belong in either of those blocks. More accurately, right? So in terms of like upper bounds, let's look at the most significant different bit, right? So we're going to compare the C7 with C0 through C3 because we already have the upper bound of like that 5th bit, but I want to see if I can get a tighter one, right? So if I compare the C0 to C3 block with C7, And I find the most significant different bit. So in this case, it's going to be just this bit right here. It's going to be the third bit. So the most significant bit at which they differ is the third bit, but you know, that's a lot tighter than the fifth bit that I saw earlier, right? So if I know that if the third bit in any particular address differs than from the prior address, and you know, they can't belong to the same block, right? In other words, 2 to the 2 is the strict bound that we have, because you know, as long as those last two bits match or are the only two different bits, they're going to belong, any potential address is going to belong in the same block. And so what we're going to conclude is that 2 to the 2, or 4, is going to be our cache size. And so the explanation that we provide is along the lines of, you know, cache access 4 helped me determine a higher upper bound or lower bound, and cache access C7 helped me determine lower upper bound. Cool. So then it says it opens up the question to all 10 accesses. And it asks us to determine the associativity of the cache as well as the size of the cache. So let's first do associativity of the cache. So I know this is not going to be a fully associative cache. And the reason for that is quite straightforward. The reason for that is we have, well, I think before we move forward, I think it would be very useful to go and write out the tag bits. Oh, no, pencil's not actually, that's why. The tag bits for each of these addresses. So this first address is going to be, I'm not going to write the hex symbol, but it's going to be C0, then I'm going to have C0, and then I'm going to have DC, and then I'm going to have C0, and then DC, C4 to C, DC, C0, and lastly C4. Okay, so those are just the tag bits. The way I got those is I truncated the last 4 bits, or the last 2 bits, and those are the numbers that you get. Great. So let's use these tags to kind of understand how things are moving in and out of the cache, right? So I knew, and I discussed this earlier, I knew that at this point, right, I had both the C0 and DC block in my cache. So when I access C4, there's the possibility that I evict something. When I access the C4 block, there's the possibility that I evict something. I don't know. So then I access 2E. So that's an address that I've never seen before. It's a compulsory miss, you know, because it's not going to belong to the same block as something I've seen. And so, great. So that doesn't give me very much information with regards to the associativity. But then I access DE, and DE misses. What does that tell me? That tells me that DE must have been evicted. So, you know, again, this doesn't tell me everything that I need to know. This just tells me that one of these 2 accesses resulted in an eviction, either C7 or 2E. However, when I move on to the next line, when I look at cache access 9, I get a hit. If this was a fully associative cache, right, the entire eviction policy would be determined by LRU. If we had a LRU that was determined like across the entire cache, which was accessed more recently, block D or block DC or block C0, right? Last time we accessed block C0 was on cache access 4, and last time we accessed block DC was on access 5. Yet what I'm finding is that DC has been evicted, but C0 has not. So that is the reason why we know it's not going to be fully associative, because something got evicted, not by like a global LRU policy. So now we know it's between directly mapped and two-way associative. This is where I screwed. I messed up a little bit last time, so hopefully I'll do this right. Okay, so how do we know that if it's directly mapped or two-way associative? So two-way associative, recall, is the idea that I have a bunch of sets, right? The number of sets I have is determined by my cache size, but each of those sets have two ways. In other words, each of those sets have two blocks they can store, and within those sets, they use the LRU policy to evict. So how does this provide us any information about, or how do we determine which one of these it is based on just these cache accesses? So we haven't looked at cache access 10. In cache access 10, we access block C4 and we get a hit. Why is that interesting? Well, C4, the C4 block we haven't accessed in a minute, right? We've performed. If I switch colors one more time, I'll switch to like pink. If we've performed 3 accesses between the last time we looked at C4. If this was two-way associative, right? Those accesses, that access pattern would have resulted in an eviction, right? I don't know how many set bits there are exactly, but what I do know is that if I, look strictly at the, binary representations of this, right? The least significant bits are going to be my set index, right? And the most significant bits are going to be the tag, right, at a certain point. However, if we kind of look at these addresses, what we find, right, is that, what if we made the least significant, just that third bit the set index, right? And so all of the other bits were different, were tag bits, right? Well, I would have an eviction because C7 would get evicted because I would still have matching, or I would have 2 accesses in line 7 and 8 that result in that look at the same set index. So then, we could expand that, but like, expand the number of sets, which would essentially double our cache size. And we could say, what if our set index was 0 and 1, right? In other words, my cache was 8 large, and would that work, right? Well, potentially, right? But the problem with that is, again, that the prior cache accesses would have resulted in an eviction. And so what this tells me, like, just I could continue this process, but what I know at this point is two-way associative caches are not going to work for the simple reason that cache access 10 must be evicted, right? Until I get to a point at which the number of sets that I get to is really high. So I actually can't access question 3 in a bubble. I need to consider question 4 before I fully answer question 3, which is why this is a little bit of a tricky question. So question 4 asks me, what is the size of the cache? I know that at a certain point, I had both C0 and DC, like two different blocks. So that tells me it's at least 8 bytes, right? So the question is it 8 or 16? So if I can show at any point in this access cycle that there needed to be 3 blocks in the cache, I could find out if this was a 16 block cache, or sorry, a 4 block 16 byte cache, or an 8 byte cache. So let's look at this for a second. Okay, so we look at, let's take a look at cache access. So in cache access 5, I brought DF in, or the block DC in, and then I performed 2 accesses and DC was evicted. That tells me that C4 and 2C, one of those must have evicted DC, right? In other words, their set index bits, right, must match up. So I look at, I'm going to switch colors to black. So, you know, if I compare their set index bits, right, or just a couple potential ones, you know, I have 2 options. I could have, you know, that is the set index bit, but we talked about in when we're talking about part 3, how that couldn't possibly be the case, because then cache access 10 would have been evicted, right? So what if it was that, right? What if our set index was 2 bits? In other words, we had, I guess it would be 2 blocks, right? Or it would be 4 blocks, right? So this is if we had 16 bytes. Well, if we had 4 blocks, then 2E would have caused 2DE to be evicted, right? Which, by the way, means that we must have a directly mapped cache, because just a singular access, 2E, is responsible for DE being evicted. So we can kind of answer these questions 3 and 4 are very interdependent in terms of the 2-way associative versus directly mapped, and the 8 versus 16 question. Because cache access 10 tells me that I can't have a set index that is just 1 bit, and cache accesses 6 through 8 tell me that the set index must be 2, right? I can't go lower. I can't have a set index that's more than that. And so I can kind of put these together. So this tells me that my total size is 16 bytes, right? Because I have 2 blocks, 2 bits of set index, which means I have 4 blocks, just 2 to the 2. And each of those blocks is 4 bytes. So I have 16 bytes. And then I now know I have 2 blocks of set index, right, for 16 bytes. That's directly mapped. Each block has a designated thing, and so we know it's going to be directly mapped. So those last 2 questions are really tricky because they're very interdependent, but it's something to consider when you're going about this type of question. All right, that's all I have for you on question 6. I'll see you for the next question 7.